Go on the road. You guys want to start with some questions from homeworks or whatnots? What do you guys think? I know the heat is broken in my room, so I apologize. Apparently it needs a part, so it may be a little while. Wear pants tomorrow. Actually, you're not coming here tomorrow, so cross your fingers for Monday. I'm a cold too. It was blowing outdoor air earlier, so you missed that. It went from like 70 to 62 in like a half an hour.
That's great.
So
What's it right now?
I don't know, but it's way warmer than it was. Yeah, I know. But they're working on it. It was a part needs ordered. It's been ordered. They should be coming. I don't know. We're trying. I apologize. I'm cold too. No more questions though. Has anybody got some non-temperature related questions anyways? No? Mary?
Do you do 77?
Sure. So 77 asks us to plot this three-dimensional point. So I'm going to start by kind of drawing the three-dimensional axes. Okay, do that real quick. All right. So I'll start by plotting making one tick mark on the x-axis, 3 tick marks on the y-axis, and I'm going to build like a parallelogram here. So this is the point like 1, 3. And now what I'm going to do is lift that entire parallelogram 2 units in the z direction. So like 1, 2. I start at the origin and lift that point. And then that point also on the y-axis I lift. And then I'm going to eyeball the other 2. Again, I'm lifting them kind of 2 units. I'm just kind of getting this in here. So that's my new plane. So the point 1, 3 that's been lifted is now the point 1, 3, 2. Is that okay?
Yeah.
Sure thing. And again, like leave the box parts in. Like that's helpful for me when I'm grading things. You can color code stuff or whatever. That's totally fine. If that helps you, I get it. But leave the box in. It's really helpful to kind of see how you did that. But that's basically what we're doing. Other questions? Ava? 80? Sure. So it's, same idea, right? It's 80. So we'll just take that and plug it in over here. The difference is that we have some negative coordinates. So again, we'll start the same way. So I'll do 5 tick marks in the positive x direction. So like 1, 2, 3, 4, 5. The y is -3, so I'll extend my y and do 3 tick marks there, like 1, 2, 3. And then the z is -6, so I'll kind of get that prepped out already. 1, 2, 3, 4, 5, 6. Okay, so there's the origin. There's those. And we'll kind of draw our parallelogram. Okay. And we're gonna, in this case, we're gonna be like kind of dropping this plane 6 units. So I'll start doing there. And then from there, then we'll eyeball these other 2. So that's probably about 6. That's probably about 6. And this one was our point in 2 dimensions, 5, -3. So this guy would be our point in 3 dimensions, 5, -3, -6. Does that feel okay?
Yeah.
Sure. What else? Happy to do some more if you guys got more questions. If not, that's okay too. Okie dokie. We'll start then. Today we're going to be looking in sections 8.6 and 8.7. So in 8.6, we're going to be talking about 3D vectors. So let's start by just kind of talking about some forms of 3D vectors to start. So component form in 3 dimensions is going to just be like x, y, z, right? No surprise there. If we want to talk about IB component form, what's going on there? Well, it's, again, just the column vector x, y, z. Whoop-de-de-doo, right? No big deal. If I want linear combination form, that's going to be x times the I vector plus y times the j vector plus z times the k vector. And again, I, j, and k are the very special unit vectors. 1, 0, 0, 0, 1, 0, and k is the new one. That's the vector 0, 0, 1. Right, so very kind of straightforward. This is exactly how things are behaving in 2 dimensions. We've just added a 3rd component to these. Nolan? Okay. Just like with vectors in 2 dimensions, another way we could describe a vector in 3 dimensions is from 2 points. If I gave you 2 points in 2 dimensions, where I say like one is the head and the other is the tail, how did we convert those into a component form vector? Yeah, so we're going to do the same thing here, head minus tail. And that'll convert our 2 points into a component form vector. So say we have some component form vector and we want the magnitude. How are we going to do that in 3 dimensions?
X squared plus y squared plus z squared.
Yeah. If you remember from last time when we talked about the distance formula in 3 dimensions, if one of our points is the origin, because in component form the tail of our vector is the origin, we just have x minus 0 squared, x squared, y minus 0 squared, y squared, z minus 0 squared, z squared. So not surprisingly, the magnitude just turns into square root of x squared plus y squared plus z squared. So if we want to talk about vector addition, say we have vector u and then vector v. How do you suppose we're going to add those 2 vectors? Yeah, we just add them component-wise. Exactly right. So we add the x components together, the y components together, and then the z component together. No surprise there, right? How about scalar multiplication? So again, let's say we have some component form vector, and in this case we just have some real number k. What is k times the vector u going to be? K times the x component? Yeah, k times the y component, k times the z component. Exactly like it works in 2 dimensions, just there's a 3rd dimension. Yay! So vector additive inverse for some vector v in component form. What is the additive inverse of vector v? Just negative v, right? Which is just a negative of each of the x, y, and z components. If we have vector addition and scalar multiplication, this additive inverse property, what else can we get? Obviously, then we have vector subtraction as well, right? Now, I'm using u's and v's all in here. If you have trouble telling the penmanship apart from your u's and v's, use different letters. Use A and B or whatever. Like, they're just letters. Doesn't matter what letters you're using. I wouldn't use I, J, and K because those are special vector names already. But, like, really almost any other letter is going to be fine, right? Some of us have better penmanship than others and can tell the difference between u's and v's easily. Some of us struggle with that, with our penmanship. I don't blame you. I am not the king of pretty penmanship. So if U's and V's are not to your liking, just pick different letters, A and B, that's fine, like whatever. They're just names. Call a different name, it still does this, this property holds. What else did we have for 2 dimensions? We have dot product. What does that look like in 3 dimensions? So if we have our 2 vectors, U and V, in 2 dimensions, we multiply the x components, multiply the y components, and add them together, right? What do you think we're going to do in 3 dimensions? Same thing, except we also have to do the z component, right? And since the dot product works basically the same way in 3 dimensions as it does in 2 dimensions, all the properties of dot products from 2 dimensions hold, namely these ones. Again, these are the exact same properties as 2 dimensions. So that all is still the same sets of properties. We're just going to list them again because they still hold in 3 dimensions. And really, these hold in n dimensions, let's be honest. What vector quantity haven't we talked about that we talk about fairly regularly in 2 dimensions, but we have yet to mention in 3 dimensions? What was that, Joe? Direction, yeah. So in 2 dimensions, how do we define the direction of a vector? We use that standard position angle, right? So all of our possible directions for our vector are angles along a circle. In 3 dimensions, they're going to be angles along a sphere. How many angles do I need to describe a position in a sphere? 2. Think about your position on Earth. You need to describe that position with a latitude and longitude. Yeah, exactly right. Same idea. Now, this is now approaching something pretty complicated and kind of beyond the scope of what we're trying to do in class. So we're not going to be talking about direction for 3-dimensional vectors, more so than just kind of discussing in generality what this would look like. Now, all of a sudden, you need 2 angle components to describe it. Actually, getting those angle components out of a component form vector is not trivial, but we're not going on to be like airplane pilots or something, so this is not core to what we're trying to do here, and it's actually pretty specialized and not something that has a lot of application past like terrestrial navigation. So we're going to kind of skip that idea. Everybody's okay with this? That's why we're not talking about direction here. So let's do just a quick numeric example to kind of connect some of these ideas together, and then we'll move on to the next set of ideas. Because this has been kind of a nothing burger of a section so far, right? Has this really been any appreciably different than anything we've done up until this point? Not really, right? It's been the natural modification to things we've already done. So, example, it says find and graph the vector w, which we define as 2 times the vector u plus the vector v, where u is the vector -2, 4, 7, and v is the vector 7i minus 6j minus 9k. First thing I would do in approaching this problem is
Draw.
I probably wouldn't start by drawing anything. I would get my vectors into the same form at least, and the form I would pick would be component form. You could put them both into linear combination form, but like y. So how do I rewrite vector v as a component form vector?
Put 7, -6.
Great. 7, -6, -9. Right? The coefficient from I becomes the x component. The coefficient from j becomes the y component. The coefficient on k becomes the z component. So then, okay, well, w is just 2 times my vector u plus my vector v. So let's see, 2 times -2 is -4, and then plus 7 is 3. 2 times 4 is 8, plus -6 is 2, and 2 times 7 is 14, plus -9 is 5. So we did the find part. There's my vector w. We're still left with the graph part. Let me go just steal that real quick. So let's go ahead and graph this. So we're going to graph this just like we would graph a point, with one small addition. We'll talk about what that addition is in just one moment when we get to it. So 3 tick marks on the x-axis, 2 tick marks on the y-axis. Kind of build out my parallelogram here. And then we're going to lift this 5 units in the z direction. And I'll just make a different color for the point that we're interested in. So there's my point. How do I turn this into a drawing of a vector, though? What's the one addition I need to include? An arrow from the origin to that point. Good job. But a pretty easy, direct chapter, right? We're just doing the same things in 2 dimensions that we've done in, or just doing the same things in 3 dimensions that we've done in 2 dimensions. No big deal there. So section 8.7 is 3D vector equations of lines. Now, remember when we talked about 2-dimensional vector equations of lines? It was fairly easy to translate the Cartesian form, like a y equals mx plus b, and to write that as a vector form, right? What is a Cartesian equation for a line in 3 dimensions going to look like? Well, that's only going to be 2-dimensional still. Like, yeah, it's not entirely clear what that would look like. And in fact, what you've described there, Nolan, won't give you a picture, won't give you a graph of a line, but rather a plane, which is not what we're looking for. It's actually not practical for us to write a 3-dimensional equation for a line in a Cartesian form, just like a xyz equation. So we really need to have a vector equation. Because in 3 dimensions, what does slope mean in 3 dimensions? Yeah, it's like, what is this, rise over run over height? Because there's like an extra way that the line could be changing in the x direction, the y direction, and then also in a z direction. Yuck. Fortunately, a vector representation of a line in 3 dimensions is fairly simple and fairly compact. So let's talk about what it's going to look like. So here's our 3D vector equation for a line. Does that look familiar? It's the same as the 2D version, right? What was R naught in the 2D version?
0.
It was a point vector, right? So any point on the line, we just kind of like vectorize it, and that can be our value for R naught, right? And then what was V in 2 dimensions?
Force.
Well, it was a slope vector, right, is what we called it, right? We found the slope and then we just vectorized that. Now, there's not really an analog to slope in 3 dimensions, but what we want is any vector that's going in the same direction as our line. So we'll just call this like a direction vector. As long as that vector V is in the same direction as our line, we're good. Everybody's okay with that? So let's look at how we do this numerically. Oops, that's not what I want. Okay. So it says find a possible vector line equation for the line through the points 5, -2, 6, and -4 or -3, 4, 1. So just like for 2 dimensions, in 3 dimensions again, there's going to be infinitely many answers to this. We just need one possible answer. There'd be 4 easy answers to get, any of which is fine. We'll kind of talk about what those 4 would look like. So we need to write an equation, R equals R naught plus VT. So for R naught, there's kind of 2 obvious choices. What would those 2 obvious choices for R naught be? The points, yeah, 5, -2, 6, or -3, 4, 1. Everybody's feel okay there? Not surprising, a point vector. If I know 2 points, that gives me 2 obvious choices for the point vector. How about our vector V? I need a vector that's going in the same direction as the line. How would I do that? There's going to be 2 obvious answers here. Yeah, exactly right. So if I take the vector from the first point to the second point, or if I take the vector from the second point to the first point, either of those 2 vectors is going to be in the same direction of the line. Doesn't matter whether it's going, you know, like forwards or backwards, kind of. They're both fine. So that would be our other option for V. So head minus tail. Or if I do it the other way, do tail minus head. What do you notice there between those 2 values for V? They're just opposite signs, right? Each component is the opposite sign. So one possible answer would be just this, where I'm just going to use the first possibility for my point vector with the first possibility for my direction vector. But there's 3 other possibilities, right? I can use the the first one or the first point vector with the second direction vector, or I could use the second point vector with the first direction vector, or I could use the second point vector with the second direction vector. Any of those combinations are a correct answer. Those are the 4 obvious correct answers. There's infinitely many of these. You would not have to supply ever more than one of them. Any of them are equivalent. Those are the 4 obvious ones that I'd expect to see on a test or a quiz for something like this. But I guess if you wanted to get like super creative, maybe you could find some other version. I would not recommend it because it's going to be like a lot more work than just what we did there, which is pretty straightforward. Okay, let's do another example. So if we have this vector equation of a line, we can do a lot of the same things that we did for a line in 2 dimensions. So let's say we want to determine whether this point lies on a given line. Right? We asked the same question in 2 dimensions. And in fact, this is part of the routine for determining whether 2 vector line equations are parallel or coinciding. Right? We do the same check if we're checking for that. So all I'm going to do is I'm going to plug in my point for R into my vector equation for a line. And then I'm going to do my vector operations on that right-hand side. So I have a scalar multiplication between the t and the vector 1, 3, -2. And I have an addition with the vector -3, 12, 7. So this becomes one vector whose x component is -3 plus 1t, 12 plus 3t, and then 7 minus 2t. For these 2 vectors to be equal, that would imply this system of equations holds. What's the nice thing you notice about this system of equations that we've written? There's just one variable. So we can just solve each one of these separately. There don't have to do any substitution, any elimination. There's no matrix that I need to solve this. It's very easy. I'll just add 3 to both sides in the first equation, give me t is -2. I'll subtract 12 from both sides, giving me 3t equals -6. And divide both sides by 3 to get -2 again. In the third equation, I'll subtract 7 from both sides, giving me 4 equals -2t. Divide both sides by -2, and I get t equals -3 a third time. Since these are all the same, we'd say yes, that -5, 6, 11, that point lies on that line R. Oops, forgot the word on. I said it. You ever talk faster than you're writing and then skip words when you're writing them down? Maybe that's not a thing unless you're like writing notes and talking at the same time, which you probably don't do a lot of as a student. But I do it all the time. It's infuriating to me. It's like, why do I make this mistake? What do you guys think about that? Is that okay? So again, all of our 2-dimensional skills we've seen so far do not change in 3 dimensions, right? You have to make minor modifications to account for a third component, but all the procedures are the same, right? Joe?
So for example, for number 103, how would you set that up?
Okay.
I, J, and K.
Sure.
You don't have to solve that. I just want to see the setup.
Yep. Let me grab the problem so everybody else can kind of see what we're looking at too. Oops. Oh, that's got a lot of Okay. Let me grab that then right there, and then we'll. So those are the problems. Oh no, that's not what I want. That was the answers. Okay, these are the problems. So that's not very helpful to us.
Wait, I think I was looking wrong. Sorry, I meant like,
No?
nah, I meant like 117. I was looking at the answers too. I meant like 117.
Oh, we haven't done that section yet.
Oh, okay.
So we haven't done that yet. That's the last section. Chapter 8 is this.
5 points.
Is the, well, it's the interaction between two three-dimensional lines, and there are actually 4 outcomes there instead of 3. But that's like a whole day, and we're not going to start that right now. But if you want to do one of these ones where it's like take our answer from this one and rewrite it as linear combination form, I'm happy to do that.
I wasn't really close.
No?
I
Okay.
think I'm okay.
You think you're okay?
I'll let you know if I have any
Sure.
questions.
No problem. No problem. So I think at this point we're good up through 114. Or no, wait a minute. You said 117 you're asking about, Joe?
Yeah.
Yeah, we can, okay, we should be able to we can do that. Let's do that.
You know how to do it, right?
Yeah. You have everything you need right now.
Yeah.
Okay. So here, it looks a little weird, but the t is just hidden inside each component, right? So I'm just going to pick 3 values for t. Doesn't matter what they are. Those would be the ones that I would pick. So for t equals 0, my point would be, we'll say r equals, in the x direction, we're going to have 1i. In the j direction, we're going to have 3j. And in the k direction, we're going to have negative 2k, which is just the point 1, 3, negative 2. There's a point.
Maybe we should do that for each of them.
And I can just do that for any value of t, generates a point. So you pick t equals 1, 2, 3, 26, 119, 10,042, 4/3, pi, square root 7, whatever you want. Now, I don't know why you wouldn't use convenient to do arithmetic numbers like 0, 1, and 2, or 0, negative 1, and 1. You know, like that's what I would do, but any values of t are fine.
So if you did like, you did 1, then it would just be like t equals 1. Just
So it'd be 3, negative 1, negative 1.
got it.
Easy peasy, right? Again, a lot of this stuff looks complicated because of the form, but what we're doing is just kind of like algebra 1 ideas, just with like weird looking stuff, where how do you get a point out of an equation for a line? You just pick a value for x and then you evaluate the y and ta-da. Here it's even easier because our parameter, t is just a parameter. So you pick a value for t and then it spits out like your x, y, and z. That's all you're doing. And you just write down the values for x, y, z, which is cool. We talk specifically about parametric equations in a future chapter. I forget if it's the next one or the one after, but that's fun idea. And this is like an example of a parametric equation, since t is not like part of the output or part of the function identity. Like t is the input of the function, that's the independent variable, but x, y, z are the dependent variables, like what you're actually plotting
Yeah.
are all dependent variables in this case, which is kind of cool. Allows you to do some pretty neat things and call things functions that ordinarily we wouldn't be able to consider functions. But we'll see that more when we talk about parametric functions. And I don't remember if it's chapter 9 or 10 or something. Maybe 9 is the geometry chapter. Yeah, 9's the geometry chapter. 10 is parametric. So that's coming. Anyways, we're stopping here for today. So I think at this point we can do 89 to 118. For Sunday, I think I'm asking for 41 to 88. And then for next Sunday, that's where 89 to 118 is going to go. And then plus the last couple of questions. Everybody feel okay on this? Pretty clear as to what's due when and all that jazz? I tried to keep the problem sets reasonably small, or at least the checks reasonably small, because there's 120 problems, and I tried to keep about 40 or so problems in a set, which is, most of these aren't too long to do, right? They're not, the story problems are probably the worst ones, outside of 119 to 122, are really the most time-consuming ones. Most of these are reasonably quick if you know what you're doing. Hey, Sadeki.
I sent you that email.
Okay, I think I fixed it.
Okay, thank you.
Yeah, if it didn't look like it, send me something. Send me it again. But I thought I did that this morning. No problem. Everybody good? I'm stopping here because the next section I'd like to do all in one setting, and I certainly can't do that with the time remaining. So you guys get some bonus time to get some work done, which I don't think anybody's going to complain about, other than the temperature of having to sit in here. So we have another day for section 8. We have a review day. I'd say at the earliest it would be the end of next week, or maybe the beginning of the week after. We'll kind of see how that plays out. Is that okay? Yeah, I'm going to pass everything back right now. You're welcome.